So hello everyone, this is Pranav Sharma from DSI BTech second year. Today we are going to discuss about cross product in light of linear transformation. So let's get started. So first let's talk about the agenda. We will mainly focus on the visual interpretation of the numerical computation of the cross product, visualize the concept of duality and apply it in the cross product to get a better feel of how the geometric interpretation of the cross product is related to the numeric computation, means how the numeric computation leads to the volume and area that we mainly discussed about in the cross product. We will also extend the idea of cross product from two vectors to the exterior product for n-dimensional vectors, and also see the use cases of these in real life and machine learning. So first, let's talk about the definition of cross product. So given two linearly independent vectors A and B, the cross product A cross B is a vector that is perpendicular to both A and B, and the magnitude of that vector is given by this equation here, which is A cross B magnitude is equal to magnitude of A into magnitude of B into sine theta. Now, generally what we are taught is that when we want to find the cross product of two vectors A and B, we write in this format where these are the basis vectors I, j, and k, and these are the components of vectors A and B along the specific directions. But have you ever thought that why, means how this determinant leads to something more physical like an area and volume? Means how this funky determinant operation involving basic vectors and basis vectors and treating them as scalars leads to a vector perpendicular whose length is equal to the area of the parallelogram. So we are going to focus mainly on that. But to reach at that place, we need some basics. So we want to stress on the fact that this is just not a notational trick. It has proper mathematics behind it. Also, we will first see about linear transformation and what it means visually, and also discuss determinant and see its visual interpretation. And we also need to understand the concept of duality for that. So what is a linear transformation? It is just similar to a function with a vector input and a vector output. We give it a name transformation as it transforms the vectors. So the convention of not naming its function is because of the transformation. Now visually, a transformation is linear when it has the following two properties. First is that all lines must remain lines without getting curved, and the origin must remain fixed in place. Now here we use the notion of lines because when we talk about transformation, we imagine every possible vectors. So in order to visualize properly, we imagine the tip of those vectors as points, and we then transform it into a grid in case of two dimensions. So let's get a visual feel of it in the next slide. Okay, so here is the input vector and here is the output vector. And when we apply a transformation, it transforms that into the output vector. So a matrix is just a transformation on any vector. Now we want the transformation for all of the vectors in the vector space. And to visualize it better, what we talked earlier, we denote it with the points as we see in this visualization. So here are those points. Now, when we apply the transformation on these points, it transforms all of those points. So they get all scattered or whatever the transformation means for those points. Now, in case of 2D, we transform those points into grid to get a better visualization. Now, so as we talked about earlier, that the grid lines must remain parallel and evenly spaced. And um, how would we describe those transformations numerically? Means if the vector, the x and y in are the input vectors and the x out are, and y out are the output vectors. So how to describe this transition between them visually and also numerically? So we only need the ith and the jth vector, which are the basis vectors in the x and y direction, to describe a transformation in two dimensions. Because every other vector can be described as a combination of these two vectors. So if we know, let's say for example, the -1 and 2 vector, if we know how it is a combination of I and j vectors, means with what coefficient, then after transformation also, as the transformation is linear, so we do not merely need to change the information set. We only need to see how the transformation is affecting the I and the jth vector, and in the same way it will affect the v vector, which is just a combination of both of them. So we can get this vector, the v vector, as a combination of the transformed I and the transformed jth vector. So as you can see, the transformed v vector is -1 times the transformed I cap plus 2 times the transformed j cap. And let's say the transformation made I cap to be 1 comma minus 2 and j to be 3 comma 0, then we can see that uh, just by multiplying those coefficients, we get the transformed v vector, which is nothing but 5 comma 2. Now what we can see from here is that a transformation, which is nothing just the matrix, can be also visualized in this form, where the columns represent where the basis vector will land. Means, for example, for this 2D transformation, this first column will give the location of where I cap will land in after the transformation, and the second column will give the information of where j cap will land after the transformation. So let's say any vector, for example 5 comma 7, when is when the transformation is applied to the vector, we can just simply multiply those columns with the coefficients and get the transformed vector. So from here, what we develop is a visual interpretation of this matrix, that how it is changing the I cap and j cap vector, and that indirectly gives us the information of how it will affect the vector on which the transformation is being applied. So this is not just a bunch of numbers, it gives us a proper visual feel of how the transformation is affecting the vector space. So next, let's talk about the determinant. Visually, what the determinant means I do know that most of you must know the computation side of determinant, but what visually determinant means is it means the scaling factor by which a transformation changes any area in the vector space. So for a 2D vector space, it is area. For 3D, it is volume. Now, a determinant of 0 means that the transformation squishes all of the space into a line or a point. Now, a determinant of less than 0 indicates that the axes have been flipped or by the transformation. So, for example, if we take the example of 2D vector space, then this flipping corresponds to uh, flipping the ith and jth vector. Because if the ith vector is not on the right side of the jth vector, then we can conclude that it has been flipped. Now, let us also see the visual meaning of determinant by the means of this video. So this square gives you everything you need. Means this is the square made of the ith and jth vectors, the unit vectors. Now, as we apply a transformation on this square, the amount by which the area of this square changes is the same amount by which the area of any other square in the vector space changes. So as we can see here, if we take other squares and apply the transformation, the scaling factor remains the same. That is, the determinant remains the same for the transformation. Now for a shape which is not a square, we can just divide it into multiple smaller and smaller squares to interpret it in the way which we have learned just now. And as it is a combination of just those squares, so even if the shape is not a square, the scaling factor would remain the same as was in the case of the unit vectors. So this is how the transformation affects the shape. Now let's move ahead. The determinant of a transformation. So now the determinant gives the scaling factor. For example, if the determinant of this matrix, as we can see, is 6, then the area will be scaled 6 times. Now let's move ahead. Now, similarly, in case of 3D transformation, just the concept of area transforms to that of volume. Means here the volume will be scaled similarly. And we here analyze the cube, means the unit cube formed by the basis vectors in the 3D vector space. So as you can see, after the transformation, the cube becomes a parallelepiped, and the scaling factor by which the cube's volume changed is equal to the determinant of the transformation. So this determinant gives the volume of the parallelepiped. And as we can see here, if the determinant of the transformation matrix is 0, then the volume squishes to a plane and the volume becomes 0. So this is an important concept which we will work more on in the next slides. That if the determinant is 0, then it squishes into a plane or a point in extreme cases. And the columns must be linearly dependent for the determinant to be 0. Now let's talk about dot product and duality. These are some of the basics that we need for our further understanding of the cross product. So dot product and duality. Visually, dot product is same as taking the projection of first vector on the other vector and multiplying it by length of the other vector. So as you can see, it would be is equal to AB cos theta, where theta is the angle between A and B. Now, this is the dot product, means you understand that we are just taking projection and multiplying it by the length of the other vector. Now, what is duality? According to the concept of duality, whenever there is a linear transformation to the lumbar line, then it is associated with a vector called a dual vector. So, let's say we have a transformation which squishes the dimension to 1D. Let's say it transforms the 2D vector space into the number line. Then the concept of duality says that it can be associated with a dual vector, and the effect of the transformation on the vector space is similar to taking the dot product with the dual vector. Means the result will be same. Either you take the dot product or a dual vector, or you apply the transformation. So the vector is such that performing the transformation is same as taking the dot product with the dual vector. Now the cross product gives an example of this process in action. So this concept of duality will be used further. Now, we know what we have learned from the previous slides, that any matrix transformation with this form, the first column gives the information of uh, where I cap will land, and the second column gives the information of where j cap will land. Now, in case of dual vectors, this information means this matrix transformation transforms it from 2D to 1D number line. And this gives the information of where the vector will land on the number line. We can see the dot product is a matrix transformation to the number line with elements as the transformed values of the basis vectors, where these are the transformed values of the basis vectors. So we can say that matrix vector product and dot product are just interchangeable, as you can see here. Now finally, let's talk about cross product. We define a 3D to 1D linear transformation in terms of A and B. To get the better understanding of that determinant, we define a 3D to 1D linear transformation. Now we associate this transformation to its dual vector. And finally, we show that this dual vector is A cross B. It clarifies the connection between the competition and geometric meaning. Means these are the steps that we will follow in the upcoming slides. So this is just an overview. So this is the defined function. Means we put a vector, and the output is the determinant of that vector with two other vectors v and w, or of which we want to find the cross product. Okay. So this is a different function, means this is not the cross product function. We have defined a function to get a better understanding. Now, a very important fact about this function is that it is linear. So as we learned before, that linear functions can be associated with a dual vector. Now, to see it as a transformation and finally as a dot product shown ahead, we associate it with the dual vector. So here is the dual vector. Now, this determinant can be seen as a transformation, and this dot product can be seen as the dot product with the dual vector. Means the transformation can be seen as the dot product with the dual vector. Now, let's say that the dual vector is P. So it has these following components along XYZ, P1, P2, P3. Now, we can then geometrically say that we need a vector P such that the dot product between P and XYZ is same as the volume of the parallelepiped formed by XYZ, V and W. Now, where does volume come in notion? We saw earlier that the determinant gives the area of those vectors, and for 3D it gives the volume. So, when we take the determinant of these three vectors, it gives the volume of the parallelepiped formed by these three vectors. So this function is in a way finding the volume of these three vectors, where x, y, z is a variable, and we need to choose this vector p such that the dot product between p and x, y, z gives the same result as the volume formed by x, y, z, v1 and w. Now we also know that taking dot product means taking the component of x, y, z on p and multiplying it by the length of p, as we saw in previous slides. Now, let's see the visualization of how the numerical computation is leading to the volume and area, and also a vector perpendicular to both V and W in cross product. So, we firstly start with the area of the parallelogram, this parallelogram formed by V and W. Now, we multiply it with length of this vector. This vector is the xyz vector, which is a variable vector. But we can see that multiplying it with the area is similar to taking the dot product. Means, let me clarify. Uh, when we find the volume of this parallelepiped, we want to multiply this area of this parallelogram with the perpendicular vector, which is the height of the parallelogram. Now, how to find this perpendicular vector? We just take the component of this xyz vector along a line which is perpendicular to both V and W. So we multiply the area of the parallelogram with the component of xyz perpendicular to V and W. Now, so this is the visualization. But what we can observe is that taking a projection of xyz on this perpendicular line is similar to taking dot product of this xyz vector with another vector which is perpendicular to V and W. So you understand the relation means taking a dot product with a vector which is perpendicular to V and W and whose length is equal to the area of the parallelogram of V and W is just similar to taking the projection of XYZ on this line and multiplying it with the area of the parallelogram. So here is where the function that we defined comes into action. Means our function is uh, our function is needing a vector p such that its length is equal to the area of this parallelogram and it is perpendicular to both v and w. So what vector p has the properties that it is perpendicular and it has a magnitude equal to the area of the parallelogram formed by v and w. So what the computation that we saw before of the determinant indirectly gives us this the components of these of this vector. Those are p1, p2, and p3, and how it relates with the concept of duality, where we consider a dual vector to x, y, z, and which is transforming it to the number line. Now let's move on to exterior product. So let's not limit our understanding to two vectors. We take it to n vectors. So the exterior product is defined as A wedge B in some vector space. Now these are the two properties that the exterior product needs to follow. First is antisymmetry and second is bilinearity. So A wedge B should be equal to negative of B wedge A, and in case of bilinearity, A wedge B plus lambda C is equal to A wedge B plus lambda A wedge C. Now in two-dimensional vector space, let's say we have two basis vectors E1 and E2, and we can express A and B in terms of their basis vectors. So A is equal to A1 E1 plus A2 E2, and B is equal to B1 V1 B1 E1 plus B2 E2. Now the wedge product has an important property that EI wedge EI is equal to 0. Now if we take A wedge B, then we get this computation. And finally, what we get is A1 B2 minus A2 B1 E1 edge E2 means in this basis we get this magnitude, and this can be tracked back to the determinant formula. Means determinant of A1 A2 B1 B2 is equal to A1 B2 minus A2 B1. So you see how the uh, this determinant is derived from the exterior product. Similar is the case with cross product. Means let's say we have three basis vectors. So A is equal to A1 E1 plus A2 E2 plus A3 E3. Similar for E for B. Now taking the wedge product of these vectors, we get A cross B with this formulation. Now this is just same as taking the cross product of A and B. So both of the forms look identical. So we can derive this cross product from the exterior product. We do not need to define it separately. And so we can also apply this definition to R cube, R4, or Rn. So this is a generalization in, onto Rn vector space. Now, what is the use of exterior product? Now, most of the computations and algorithms in ML are restricted to linear algebra. Means we do not express geometric problems with the help of geometric algebra, but the main motive of discussing all of this is that geometric algebra can also be a powerful tool in ML and pattern recognition, especially when dealing with geometric data such as point clouds and 3D object recognition. Means you cannot just use R2 space and dot products to act. You cannot just use a linear transformation to actually analyze the 3D objects. We need more geometric understanding of those cross products and linear transformations to apply it on the 3D world. Means, for example, point clouds. Point clouds are set of 3D points that represent the shape and structure of objects or scenes. So, for example, in image recognitions, these are provide an elegant way to represent these points and their relationships. So each point in the image can be represented as a multi-vector in in geometric algebra, which allows you to encode position, direction, and other geometric properties in a single mathematical structure. So for robotics and 3D computer vision, this is really important. And we can also use it to find intersection and projection. Means geometric algebra simplifies the geometric operations like finding intersection between lines and planes or projecting points onto planes. And these have a crucial role in computer vision and ML. Now the geometric features. Geometric algebra enables the extraction of meaningful feature from point clouds. Means the same point that we discussed, that from the image it can extract meaningful features from those point clouds, as the images are 3D and we cannot just use 2D formulations to analyze them properly. And it is widely used in many fields, not just robotics, uh, because computer vision is used widely, and also in case of self-driving cars, where we need to analyze 3D data and the car needs to uh, modify its actions on the basis of the response that is receiving from the environment. And these features can capture important geometric characteristics such as curvature, normal shapes, which are valuable for object recognition. So, thank you everyone. These are the reference videos and papers, also blogs from which I have studied this content. So thank you everyone.